on something called thread per core, or TPC. This is basically our plan to transition Cassandra from a staged event-driven architecture with lots of thread pools to something that's event-driven with a small number of threads. So I actually don't have time to talk about why that's a good thing. I'm just going to talk about what we've done so far and kind of what's coming next. One idea that we're kind of trying out for a prototype is to use a set of tasks for different operations that sort of have a state machine-like structure, where the transitions in between the states happen at points like where we might need to do I/O or acquire a lock. Something where you need to defer control back to the event loop so it can proceed on other tasks and not get blocked on those long operations. So if you look at Cassandra 10.993, I just pushed a branch last week and pointed out a couple of classes. So for example, there's a write task class that handles a single mutation or a batch of mutations. And there's a couple of points where it needs to yield to the event loop. So one is commit log segment allocating space on the commit log segment. The other is waiting for the commit log to be synced to disk. So those are a couple of spots where we potentially need to return control to the event loop and wait for some sort of event to be delivered so that we know that we're ready to allocate on the commit log segment or it's been synced and we can proceed on that task. So some of the other classes that are in place there in that branch, of course, we have our own event loop to handle these tasks and the different types of events. Besides the write task class that I mentioned, there's a Paxos write task that's for the most part complete. And there's also been some initial work on single partition reads. So it actually runs stress. Stress works on it, at least for writes. We just see some dummy tasks to handle things that don't have an asynchronous version yet. So what's coming up next? We need to kind of decide if we actually like this API versus some of the alternative proposals. If it does look good, then some of the next steps will be taking our event loop and figuring out a better way to integrate it with Netty, because of course Netty has its own event loop for handling I/O. And so right now Netty is just triggering a cycle of our own event loop every time it runs. So there's a bit of overhead there. So integrating those, maybe combining them into a single event loop is the best way to do that. For the rest of the write path, we still need to handle counters and materialized views. Those are a little bit more complex. The read path is kind of interesting, mostly because the Linux asynchronous I/O, it basically doesn't work. It blocks unless you're using XFS with just the right configuration. So rather than require users run with that setup, Brandon wrote us a in-process page cache. So we will first check that. If we get a page cache hit, then we're good to go. Otherwise, we'll defer to a thread pool to handle that blocking I/O for now. And then last, we can actually start to make some optimizations by splitting up data and data structures, perhaps by token range and sort of pinning that data to specific threads. So that allows us to avoid locks in some case. We're using data structures that are suboptimal because they have to be thread safe. So those sort of optimizations would come after that. And that's pretty much it.
Andres is up next.
Oh.
Andres is up next.
Andreas is on next.
And then Shogo and then you, Jonathan.
But I like the eager attitude. That's good. Keeping it real. All right. So do you need to see the screen? Okay. Why don't we do it right here then? Yes. There we go.
Well, I'm Andres de la Peña and I work for Stratio, and we are going to speak about top key queries and paging over index sorted results. Cassandra 8717 introduced the ability to do top key queries over results sorted by a secondary index. Top key queries are those retrieving the k-best results from the total. And the way it works is that the coordinator node sends the query to all the nodes in the potentially all the nodes in the cluster, and then each node returns its k-best results, and then the coordinator resorts the partial results and then returns the globally better results. And the drawback of this is that that all the nodes are involved. We can avoid this if we direct the query to a limited group of partitions. For example, in this table, we have stored purchase orders where the primary key is the data. And we are returning the results sorted by amount to retrieve the 10 most significant orders. And in this case, we are only touching 2 partitions. However, this doesn't work. And this is so because this query is translated to a group of single partition read commands, which is not a read command, but a read query, and it hasn't the post-reconciliation processing method, which makes the magic for the top query. And we are overcoming this problem with intercepting the query with a custom query handler. This to a modified storage proxy. And it would be nice to solve this at DX and have the post-processing method in all the queries. Okay. Another nice feature that is not supported is paging over top key queries, which really is a real order by. In this example, we will present sorted views of another table. This is obviously very useful. And it's important to note about sorting that this kind of sort could be more complex than the sort provided by the clustering key. It could be distance to a point or something depending on the query. And also it allows to sort to over data sets larger than a single partition. The reason why this don't work is because SQL paging only tracks the last visited row, and this last visited row is used to calculate the next token range. And in some way, the last position and the data range are mixed. If we want to page over different sorting, which are not the partition, the token, partition key, and clustering, then we should iterate inside each import subrange. This way, the paging state should track the last visited row inside each token subrange. And also, the index should receive not the new subrange, but the original token range or the data range and the position of the last visited row. Again, we are doing this with a custom query handler and a modified storage proxy. And the solution is quite dirty, and it would be nice to have support either from Cassandra to all custom implementations. And that's how the 2 proposed changes. The first one, which is quite easy, which is just to support the in operator with top key queries, and paging over index sorted results, which is a more complex change, but I think works. and that's thanks for your attention.
Hello, I'm Shogoshi, Japan, Cassandra operator, and I am creating chef recipe for automated deployment system. I am very excited to be here, and it's a great honor to me to talk about how to manage 30,000 Cassandra connections. Again, I am a Cassandra operator in charge of creating chef recipe, and I and my team member are trying to send a patch to OSS Cassandra community, and I contributed to Cassandra community thanks to the area you watched that. This is today's agenda. At first, I will talk about the problem is, what the problem is, and share the solution to it. And I will try to explain the consequences in the final section. And what's the problem? The problem is Cassandra process goes down if too many client processes connect to it. In this example, please assume there is 200 client machines and Apache web servers, pre-fork models are working on them. In the environment where so many requests come to client machine, like advertisement platform, we set Apache Max client value to 128 in order to make the most of computer resource. So in this case, each client machine has 128 Apache child processes constantly. And each Apache child process creates two connections to one Cassandra node. First one is used for request, and second one is used for heartbeat. This means one Cassandra node has to handle 51,200 connections to reply to all the client machines. Why can this be a problem? It is because in my company, Max Open Files process is set to 32,768, and it must not be changed in terms of OS performance optimization. Please look at this. You can see the console log that says too many open files error happened by opening SS tables, and Cassandra process went down. This graph shows Cassandra process goes down and the number of connected clients declines significantly. you can see the number of connected clients increase again. It is because the Java daemons master restarts the Cassandra process. But same thing will happen soon after the restarting. So what should we do? We cannot adjust the patch max client values or max open files. We have reached the solution, Cassandra proxy. The basic idea is connection pooling, and Cassandra proxy works in each client machine and makes connections with each patch child process. And he can pass the all of the client connection, client requests, and heartbeats in the machine to Cassandra. So let's take a look at how the problem is solved. There are 200 client machines, and each machine has 128 patch child processes. No. Cassandra proxy can negotiate with all of the child processes and make them as one connection. Cassandra proxy sends client request and heartbeat to Cassandra node. So, thanks to Cassandra proxy, there are only 400 connections that one Cassandra node has to handle. As you see, we can solve the connection number problem thanks to him. But you may concern the consequences with Cassandra proxy practical and competent enough to be available in production environment. The answer is yes. Our stress test has revealed that Cassandra proxy is so capable and that can send requests and receive response within only 1 millisecond in 95% time. This test also shows that Cassandra proxy can send at least 300 requests per second to Cassandra cluster. Please let me mention that the target of this test was not Cassandra proxy, but the cluster. So we expect Cassandra proxy to have more throughput capability. Now we released Cassandra proxy to production environment, and 320 client machines and 33 Cassandra nodes are working in each data center. The cluster processes about 3,000 requests per data center, and the number of requests per second will be 100,000 in the future. This time, we implemented Cassandra proxy for ourselves and are using it internally. But if possible, we would like to send a patch to OSS community to make Cassandra proxy one of the data status GPP drivers functions. This is the last slide. I hope you found this interesting, and I'm looking forward to hearing your feedback. Thank you so much.
Yes, this time it is. So, you gonna be over here? Wherever you really? You're using your tongue? For presentation, you don't have a
No, I'm
presentation.
not.
I was gonna say, IntelliJ has a presentation mode,
Yeah.
and it works very quickly. Okay, that's good.
All right, I'll try to keep this one quick too. So this is a project that kept me up many nights. I've been thinking about testing methods and feedback loops for a long time, and some of the work that we've done since I've been data science has kind of inspired me. So this is a consolidation of those ideas into a project. This is an independent project, but the motives are squarely around trying to figure out how to make our those testings quickly and with high singularity possible. So this is what we normally see. You go into a customer environment or the user does some testing. They do this over and over until they get tired. And the results are whatever they happen to do. It's a very reactive process based on what seems to be the problem at a given moment. There aren't really a lot of ways of capturing a way of interpreting and gathering results from one environment, one test environment. Time-intensive manual effort. We don't have a codified method. We have low signal fidelity because of that, and we have a high feedback time. But really, it means we don't have a vehicle for talking about these methods. We don't have a way to capture approaches for getting a specific result from the system that we can reuse later. Like this. This is something you would ask a person to do. And if you ask 5 different people to do that, they'll come back and give you some answers. But the consistency of how it was done is going to be very low. Or this. These are things that we would like to be able to do automatically. We want to increase the amount of information we can get, the specificity of it, and reduce the time to do that. Reduce it. We'll get to that. This is not a stress tool. This is designed to do something a little different. So we'll get into details. This is a problem itself. We need a tool that focuses specifically on that type of high-level question and thinks about how you can make it possible. We need part of the system to be expressive, the part that allows you to try a different method, a different script. And we need the other parts to be as fast as you would expect any application data access layer to be. So this is the name of the project. It is an independent project. It is effectively at the incubation stage right now. It looks like stress in some ways, but it isn't meant to be stress. It isn't meant to replace stress. It's really meant to be another tool. We have so many kinds of tools that we need for testing because there's so many kinds of testing that we need to be able to do. We want to automate iterative load testing, make it easy to characterize system performance, and make efficient analysis possible. But the focus really is on dynamics of loading and performance. It's a simple sandbox that executes activities under controlled scripting with metrics included. It's a national sandbox. It's JavaScript. You can run whatever you want to. Sorry, but it's JavaScript, right? There aren't very many tools that integrate so well with Java 8 as a real scripting language and do such a good job. You can cross-call between Nash 1 and Java 8 really effectively. We have a lot of ability to customize the sandbox environment to make that scripting environment really like a DSL. So
I love exactly the end times.
what was that? I didn't get it.
I said I love it exactly the end times.
Oh. All right, so it executes activities. Go it differently.
I'm just making a job description.
Yeah. I could redo the white presentation. It executes activities. An activity is it's a workload that's defined by a driver type. They have their own executors in the runtime, but the sandbox is the outer controller. The sandbox, the script, the sandbox directs everything that happens. Client-specific drivers in the runtime are discovered if they're in the class path, CQL could be just once, working and so on. The idea is that you should be able to dynamically run mixed workloads from one control point where you have an internal feedback loop. The activity types have plumbing for eventing from the control level so that you can change the way the activities behave. The activity types themselves have to be written to receive those events and modify the behavior. But the core runtime has an example of what's called diag. It's the default activity type, which is just an illustration of unbundling, repeating its update time and showing how that works across many threads. So yeah, I know that I'm going to get a lot of flack for this. It is sequentially evented through to the executors to modify the threads active for a given activity instance. But it's really concise. And if you really don't want to use this, stay away from the one or two namespaces in the sandbox you don't want to do side effect assignment to, and just use the methods and setters if you really want. It's not going to make a big deal. So metrics included the same names that you give activities, the aliases, as are required, are used in the metrics plumbing and naming in the sandbox. So what this means is, since you have this input and output type of control loop within the main JavaScript, you have the ability not only to automate iterative testing across a set of parameters or tuning to a particular goal or finding a particular answer. You can also do it in the same runtime process, as long as you account for feedback time, history system, all this kind of stuff. So, yeah, ending is part of it. It's a conceptually simple starting point. Engine block doesn't really do much, but the things I just told you about. It doesn't have a CQL driver. It doesn't have a Spark driver. The whole point of it is to give a very specific starting point for building a testing tool. The script can be generated automatically if you use the command line arguments that provide default activity type initializers to create the activity instances. There's always a natural script controlling this, but there's a CLI form invoking it. And it's just an engine. It doesn't know much about applications. They work for different kinds of people. People who have the need to just test something from a script someone gave them. People who want to write those scripts. People who want to write the drivers, and contributors can involve. So this tells you how the internal loops work. It's pseudo-functional. It's friendly to a few ideas, but it's not strictly a few. It essentially, each thread in an activity takes an input, applies an action to it. This is a visual representation of that. On the left, we have essentially an atomically accessed sequence. On the right, that's my symbol for actions. This shows what it looks like if you compose a rate limiter into the atomic sequence, which can be used for target rates, etc. This shows what happens when, or what you can do if you need to put in some type of mapping from the sequence to a data set. That's where you put your generator logic. And this is just an example config from one of the tests that is a CQL binary. So there are different aspects of it. It's an active development. It's not ready for wide use. It's here if you want to look at it. It's still baking. I want to say one more thing. There are different aspects of development that I want to get into that I am asking for permission to get into. I have other duties as well, but the idea is that if I get my wish, the core will be open source as well as the CQL driver. So the core is open source. the CQL driver is something I would love to be able to share. So there are other things that we may be able to add on to it as a value enabler for POCs and things like that. That's the status of it. So if you have questions or want to talk about it, fine.
So I was going to do no slides, but Tyler beat me to it. Now I
It's just
can't,
not cool anymore.
right? It's done. It's been done. So I do have slides. I wasn't joking about not intending to do slides. The slides that I have written were I'm working on a presentation that I'm hoping to present at the summit. So they're not designed for you guys. And I'm blinding myself in the process. My kids, kind of a big deal with them. My name is Eric Stevens, by the way. I am principal architect at ProtectWise. ProtectWise is a network security company. I guess I can't do presentation. Okay. We're a network security company. We're based in Denver. We do a lot of really just network forensic analysis, and we do a lot of big data search kind of stuff. One of the problems that we have in security space, and because we're a multi-tenanted system, is our customers get to they provide us a large amount of data. We do about 168,000 writes per second today, going up. We get new customers all the time. But they pay us for retention of that data. And so, of course, they get to change their mind. Deleting data when a customer leaves the platform is important. It's expensive. And TTLs don't work for us because the customers get to change their mind about it. Tombstones don't work for a couple of reasons. So let's talk really briefly. Again, I apologize if these are simplistic in certain ways. They're not really meant for this audience. Tombstones can surgically delete data. They're easily reasoned about from a read perspective, but they're bad because they increase read and write I/O pressure. They do not let you reclaim disk capacity. If you're ingesting 168,000 records per second, then that adds up really, really fast, even if your records are really, really small. And if you have a really gigantic grab bag of data, it can be hard to locate the correct records to them. TTLs for our customers, they're awesome because you can just write the record and forget about it. The data goes away eventually, for some definition of eventually. But once you write a TTL, you can't change it. And if you write to a row and you do partial updates on that row, the TTL values may be consistent across those rows. And actually, TTLs may not reclaim space as quickly as you think they will, for a lot of the same reasons that tombstones don't go away as fast as you think they will. If you have TTL only part of a partition, it sticks around forever, in case you didn't know that. So patch review, again, not for you guys, but very roughly, if you write a record on the far left of this time moves forward to the right. If you write a record all the way over here and you write a delete over here in this little SS table, then you have to wait for compaction to catch up with that record before it'll eventually go away, which if you are talking for us, it's like often a year, which means that it could take a year and 6 months before our data actually gets, this space actually gets reclaimed. Really, really bad for us because in addition to us having to pay for the disk capacity and the compute capacity that's required to maintain the disk capacity, we also are entering the federal space, and one of the problems in federal space is something called information spillage. And in the case of spillage, which is something that's not your fault, your customer accidentally put something of the wrong classification, Hillary Clinton's email servers, put something of the wrong classification in the system, you have to be able to guarantee that the data is destroyed. Guaranteed. No longer at rest anywhere, even in SS tables where they're masked by other data. Well, if you're relying on tombstones, you can't do that, right? To destroy that, you have to destroy your entire cluster, which means you have caused an outage for all of your customers, whether they're them or not. So when you do write a tombstone, this stuff's not really written for you again. I have a little demo here for showing that when you tombstone data, until that tombstone catches up with underlying data, the underlying data is not reclaimed. So I just insert a couple of values on a single partition key, validate that I get the right value back, and then I delete it and I flush in between each. And so I have 3 SS tables. 1 has a record, 2 has a record, 3 has the delete. If I compact together, there's a data at rest. There's the delete. If I compact those 2 together, I get a 4th table. This guy here, you would hope that the delete that exists in 3 would therefore reclaim the capacity in 4, and it does not. It's still there until 3 and 4 compact together. That data still sits at rest on this. So, okay, moving forward. You guys, I think, can reason about this pretty easily. Compaction. Everybody loves to talk about compaction these days. Really exciting stuff, right? It's totally easy to reason about. Yeah.
Well, it is.
Let's do that, Jeff.
I've been working with Jeff on this in part. He's been looking at some of our code, and he's experimenting with it too. This is a deleting compaction strategy. What it is this is not try to change the nature of whatever compaction works best for you in terms of managing your data at rest for your read and write performance characteristics. This is a wrapping compaction strategy. It uses whatever your preferred compaction strategy is as a child strategy, and it intercedes. So it doesn't change the formula there, but what it does do is it evicts records at time of compaction in the same way that tombstones eventually come out of your data, or data would get evicted during compaction of a tombstone with the underlying data. So at the next time a given table compacts, anything that should have been removed from that table doesn't survive into the new SS table. Basic idea. So you can also, deletes are always a little bit worrying because you screw it up and you've destroyed data in some way. So we added an option to have a deletion backup directory. And so any records that are evicted during compaction can get, if you want to, can get shuttled off into SS tables in that backup directory. You realize you totally screwed up and just deleted customer data. You can copy it back in, do no true overload, and it's back. Or if your topology has changed, then SS table loader. And then we wrote several base classes of different ways to approach deletion philosophically, different methods for different use cases, and then we made it all configurable. And so you can either extend one of the base classes, or we have a few implementations. And so here's what it actually looks like. I'll try a table with a deleting compaction strategy instead. You can provide an underlying compactor. So in this case, it would be size tiered, or in this case, it would be level compaction, and then all the rest of the options just pass on through, just like you would normally expect. But you can also do, and I don't think I have a slide for that. You can also do, for example, we have a late TTL deleter or convictor, and so you set the convictor on the table, and the convictor for the late TTL just takes a single additional parameter that says what should the effective TTL be, and it looks at the right timestamp, compares it, and then any records that were written more than that ago get evicted during compaction, which means that you can change your mind about TTLs. That's a very simple one. We also have some pretty cool rules-based ones where you can describe the characteristics, some more diagrams for a less nerdy crowd. I think that's almost the end of my relevant to you guys slides. So you can also, in addition, we have a few other ones. We might have something in here. No, probably not. So there's a rules-based deletion convictor. You can say, based on the partition and cluster keys, you can establish a set of rules, a set of and where clauses. You can load those into a Cassandra table, and you can actually provide a select statement in the compaction options that describe how to locate the deletion rules for this table. And then as long as you are careful to do things like put your deletion rules all in the same partition, you can even achieve atomicity at the updates without even having to resort to compare and set. So it's configurable. It's meant really to address a very specific problem for us, but I think that a lot of people in the Cassandra industry at large struggle with deletes, and there's
Especially bulk deletes, which is
yeah, this is really good at bulk deletes in particular, and it's actually faster performing than traditional compaction because it evicts records that don't survive into the target SS table. So compaction is often performance bounded by the write pressure, and so you can reduce write pressure by evicting records. And on top of all this, and I didn't really cover this in my other slides, we also make sure to keep the indexes up to date. So if you delete a record from the SS table, your index data gets cleaned up. And all of this, one of our design constraints was this has to exist exclusively inside the constraints of a standard compaction strategy. It cannot do something different. It can't like change the underlying thing. It sits in purely vanilla Cassandra as a compaction strategy with no new libraries, no new dependencies, and no new underlying changes. Drop the jar and you're done. 58 kilobytes.
Did you publish that?
Not yet. I'm happy to make this source code that and if you want to I'll get this far. We're expecting to finalize the code kit around the summit, but
Right. All right, it's good enough, I guess, everybody. So hello, everybody. My name is Stefania. I think I know almost all of you, but not quite everybody. I also work for DataStax. I've been working on Cassandra open source for about 1.5 years. And 3 months ago, I started looking into optimizing bulk reads. The umbrella ticket is 9259. By bulk reads is actually a pretty simple problem. In principle, it's just about optimizing the query that's shown there. It's a select of a bunch of columns between 2 token ranges. That's it, where potentially could meet the entire table. And we're also optimizing for local data at consistency level 1. So the idea is that the client, typically an analytics tool, would be co-located with the Cassandra host and just square directly the correct replica and get the data that's local to that replica at CL1. So because when that happens, we're able to actually do some optimizations. What we've done as a first thing, we created a benchmark for measuring how long it takes to load data from Cassandra into Spark. We use Spark as a typical analytics tool. What the aim was basically to compare how well Cassandra does compared to files, which are stored on HDFS. So we use CSV files, but also we use Parquet files. I'm not sure if everybody's familiar with Parquet. It's just a columnar on this file format, which is very popular in analytics. The way we measure how long it takes to load data is by performing a very simple Spark operation. So we iterate across rows. For each row, we calculate the maximum between 2 columns, and then we calculate the global maximum. The reason we have to do this sort of tricks is because if we simply count the number of rows, Parquet has that information in the metadata, so it wouldn't be fair. We also iterate in 2 different ways. The first way, we use RDD, Resilient Distributed Datasets, which is a basic Spark construct. In this case, we just load all the data from all the table data from Cassandra into Spark, and then iterate over each row, and then do our calculation. Whereas in the second way, we use data frames, which is another Spark construct, but is more based on sequence. So in this case, we will push the predicate to Cassandra, and we'll tell Cassandra to only select the columns that we're actually interested in. So we wanted to measure both approaches. One is more data intensive, the other one is less data intensive. It was interesting to compare the two approaches. Initially, we had 4 schemas, of which 2 ended up being interesting, different enough. The first schema has 1 partition key, 1 clustering key, and 10 value columns of type integer. The other schema also has 1 partition key and 1 clustering key, but unlike the first schema, it only contains 1 big blob value column, and it's actually the client that will decode this value into 10 integers. And for the records, schema 2 and schema 4, they're not shown here, but basically they were the same, except they didn't have the clustering key. They just had the composite partition key, but it turned out that the performance was very similar. So we're only going to compare schema 1 and schema 3. So once again, schema 1, 10 integer columns, schema 3, the client decodes the values client side. So here are the results for the first schema, the RDD test. On the left, Parquet, as you can see, by far the best. Sorry, I should say that the numbers there are seconds. Are seconds, and basically it's how long it takes to load 50 million rows into 5 nodes, which are running on NGCC, Google Computing Engine and 1 standard 8 machines. So each virtual machine has got a Cassandra, Spark, and HDFS node running on the same machine. So we can see on the left Parquet doing really well, around 5 seconds. CSV files also not bad, 11 seconds. Cassandra before, that's Cassandra trunk of a few weeks ago. Not doing so well. I mean, even CSV files are much faster. Cassandra after, that's also trunk with 2 proof of concept patches applied. One in the client side, one in the Spark connector, and one in Cassandra itself. Improvement, still not as good as CSV, but at least starting to be, at least sort of comparable. Quickly, the other results really, this is the same, again, schema 1 with the data frames. The biggest difference to note here is that Cassandra is much faster. So what that says is that when the client itself decodes the values, is faster than Cassandra will give the values. So again, after the improvements, much better now, same level as CSV. So I use
We edged them out.
I have one confession to make, is that the data frame CSV test actually, I think it's just the Databricks Spark CSV module. It's a bit slow, so. Again, quickly, schema 3, similar results to basically a significant improvement before and after, sadly still slightly slower than CSV. And lastly here, we are better than CSV, long last. Okay, so basically, what did we do? Like I said, it's two main optimizations we've done. The first one is client side, and it wasn't all Cassandra's fault. It's actually also the client that wasn't decoding rows as quickly as it could have done. So what we did really was we reduced CPU cycles when decoding rows by avoiding to do stuff. Basically, if you can do something once and not for every single row, then that helps. That's what we did in Spark 383. Cassandra side instead, that's where my focus is. I'm still working on Cassandra 11521, where we will finalize the proof of concept. So what we did is basically, when it's safe to do so, when we only need local data, we bypass the storage proxy completely. We just go straight to the partition range command and just get the data like that. But also, as we know, with paging in Cassandra, typically the client requests one page, so we open the iteration, at the end we stop and we send the result back, then the client requests the next page, and so forth. What we do here instead is we keep on iterating, we keep on going, and when we have a page ready of results, we push it to the client asynchronously. And that's what really makes the biggest difference in that not only do we bypass storage proxy, but really we keep on going. We don't stop the iteration. We don't have to redo the disk 6, all the stuff. There's a lot of stuff going on when the iteration is stopped. So lastly, those measurements were done with proof of concept patches. They will have to be repeated, and we hope to confirm the same results, if not better.
I actually think Spark C3, I think that's already done, actually checked.
Yes, last week,
And
yeah.
it's like they did the 1.6 connector.
Yeah, for sure, yeah.
Yeah, it's really good observation.
There will be another small Spark connector patch to actually enable the Cassandra side optimizations, but it will be very small. Okay, so moving further, we got one more thing that we can certainly do. That's 11622. That's optimizing the SQL format. SQL on the wire format is still a bit wasteful. So that's definite. The rest at this point are just ideas or some old tickets which are there and we may consider revisit or maybe not. Perhaps if anybody's interested, we can discuss further tomorrow. But really what would make the biggest difference, in my opinion, to really get to the same performance level as Parquet would be to have a columnar format, at least on the wire. Probably that's, but I'm not sure. But it's probably going to be another ticket or something. Or it's also interesting to mention something called Apache Arrow. It's a new project, and basically what they want to do is to have a common memory format that can be shared between data stores such as Cassandra and analytics tools. So that's quite interesting and something to follow. I believe this is it. Thank you so much.
Last talk of the day, guys. And of course, we saved the best for last. Everyone knows it. You all know it.
There's still donuts in the bucket. No one's leaving until.
Hang on. First time using Linux over this interface.
Oh, yeah. When did you switch to Linux? Are your slides going to be on that way back?
Oh, man.
Is your slide back or what are your slides?
That is a very, very great color. I'm impressed with that. How you can get away with that?
Hey, Stefania, how did you switch the video?
Settings, display settings. Right click and then display.
Hang on. I got it.
Oh, yeah.
There you go. There you go.
Yeah. Linux! Oh, God. Hang on.
Can you just drag it to the other desktop?
Stop.
That's a better picture. Oh, yeah.
Okay, wait. I'm almost there. Now I gotta get the Wi-Fi working. Hang on.
We can't have everything. You should just sound here.
Nice. All right. Well, whatever. I can. How do I get the arrow over there? There we go. Okay, hang on.
All right.
We need to change it then, right?
Okay, so 2016 is not the year next year. Next year.
There's always
always next year.
Can I have someone else's laptop?
There's never time.
I have a solution for you. Plug that in. What? Plug that in. Plug what? Plug this into that.
He's gonna tether.
It's gonna tether you.
You gotta say today.
It's a real tether. That's pretty impressive.
Yeah. Deletion.
Run up, Brian.
Oh,
Only half a bucket left. There you go.
Do whatever you need to do to connect to that. You can't find the internet, I bring the internet to you.
Hey Jake, I'll just hold your laptop up.
Alright, I was just gonna be like that. Okay.
Alright, 3 minutes up, 2 left.
Now, my name's Jake Luciani, and over the past 6 years, I've probably broken each of your clusters with a bug I've written or something. I'm known for such bugs as going from bytes to byte buffers. You know what I'm saying? From the stress tool. What else? My break. Yeah, all sorts of So
Solandra.
yeah. So now I cannot even use my keyboard. So what I'm here to talk about is so the only thing I'm really allowed to do is like tweak little things. So what I've been focusing on in the past month or so has been streaming and compaction, trying to improve those things. Those seem to be our 2 biggest performance issues that most people complain about from an operational perspective. So, streaming, why is streaming slow? When you stream a file to a central node, say for example, you are bootstrapping a new node, each replica that's sending to that new node is sending one SS table per at a time. So let's say it needs to stream 50 different SS tables. It streams the first one, and then the second. So there's no parallels in there. And then at the same time, we only stream the data component, and basically the new bootstrapping node needs to basically write a new SS table. So it needs to add the new Bloom filter, create the index entries. So there's back pressure applied to that streaming. So when you're like watching on your network, you're like, why am I only able to send from like my random replica to this new bootstrapping node at like 20 megabytes a second? So that's the reason why. So what can we do to make this faster? One thing I noticed is pretty interesting. I wrote a test to generate 10 million very small partitions in an SS table and then stream it locally to itself. And if you look at that, that generates what?
You can't shoot this slide.
Thank you. So what you'll see here, what if you,
No, we don't see.
okay. If you could see, you can see that this is a. Sorry. This is like a 64 megabyte SS table being sent. When it sends it, it actually generates about 30 gigs of allocation garbage. So that's an interesting observation in terms of the amount of garbage that Cassandra generates just for doing something as simple as streaming. So trying to go through and fix these things, what can we do? So the ticket that I mentioned at the top, which is in for 3.6, improves streaming performance by 25%. Now this is not like that there was one obvious thing that fixed. There's actually a whole bunch of little things. And the main ones are, Netty has this thing called a fast thread local, which is, since we have so many thread locals in our like read path and write path, and SS table writing, basically for tracing data and all sorts of other things. We're always checking read locals, thread locals. So fast thread local is like a very custom thing for a fast local thread that can have a fast thread local. It improves the performance of thread locals by like 50%, which for us improves things by like about 5%. Now the other thing we do is when we just in terms of the amount of thread local gets, we're checking all the time. The next thing is when we write to an SS table, this is something that Jason mentioned before. We have this like first we figure out how big is the message, and then we write the message. But in order to figure it out, we have to like check the byte buffer length, which does a bounds check, and then you do this other check that does all these extra work, and you're actually doing the same exact thing twice. So rather than do that, if we write a CQL row into memory and then check the length of that buffer, and then write that length in the buffer, that actually is about another 5%. And then for our stream histogram, which is what's collected during streaming, there was some just silly things like the byte, the Java autoboxing, which is horrible, was going through and basically creating a whole bunch of extra allocations, plus going through that list of really hot allocations and either recycling them or just reusing them. That improved things by another 10%. And finally, on the read side of the press stream read iterator, there was like a missing method call that improves things. So that's that. But there's also a lot more that we can do. For example, the byte buff, the bloom filter add is actually the #1 profile hit. So one thing that we can do that's pretty simple is if we make the bloom filter, I didn't say byte buffer, the bloom filter adds, if we could make those asynchronous across cores, then we can basically get rid of that bottleneck, because for each partition, it basically adds to the bloom filter. It updates the index list. So if we made that a asynchronous operation, we can improve that. Something like there's another ticket for serialization getter get type, which is kind of a strange method. But anyway, that's the #2. And the #3, which is actually really the biggest problem, is our use of byte buffers, which has a benefit, but at the same time, it's got a huge cost. The Argona project, which is like something that Mark Thompson does, and Netty has something similar, but I don't think it's quite as good, is they're basically a re-implementation of the byte buffer class, and there's they're basically reusable. You can also create like one giant byte array and have that shared, and have a whole bunch of byte buffers share that single byte array, right? So you can basically create your own heap on top of a byte array. And it also gets rid of all the bounds checks. So those are like a lot of the things that we waste time doing inside of Cassandra.
Did you put byte buffer in the first place?
Yes. Yeah, no, but that was anyway. So the next thing, so that was streaming. The next thing I'm focusing on is compaction. And since you all love stress tools, I built a new one for you. It's called compaction stress. And compaction stress is very similar to okay. No, it actually is kind of simple. So the thing that I like about the stress tool is the YAML file, because it allows you to give like any CQL schema plus this distribution no one can understand, and which I set up a topic tomorrow. You can all sit down with me and tell me how to fix stress in this whole thing, so you can make it simpler. But anyway, but what it basically allows you to do is, instead of writing a stress run to write a whole bunch of data and then compact it and then wait and have the nodes coming up and down, you can basically just like offline run compaction stress write to this directory with this schema, go, and write 5 gigs using 5 threads, and it will write using 5 threads just offline SS tables to a directory or multiple directories using whatever compaction strategy you have set, or not compaction strategy, but whatever schema you have set up in the YAML. And then at the same time, another offline, you can apply compaction stress compact to those same directories with the same schema information with whatever compact strategy it has, using however many threads you want, and you can either do background compactions or foreground compactions. The reason why I did this is because in order to study compactions and all the different types, And instead of writing a whole bunch of stress profiles and this and that, I figured this was a very strict, easy way to like get just what we want. The next thing is flame graphs, and I don't know how many of you guys use flame graphs, but they're actually pretty powerful. They're more powerful because this is sort of the de facto flame graph, but and this is obviously hard to see. But when you look at one of these things in yellow, that's actually like a Java method call. The problem is you don't really have context because it includes all the inline code. So one of the things that I worked with Brendan Gregg, and thankfully I got to use my favorite language, Perl, and it fixed the flame graph so that now you actually get inline method calls as well. So you can see at a very fine-grained level, like across the Java code, across the JVM, and these are actually resolved addresses that you can see. And you can actually run this per thread. And this is what's great about this tool, and this is something that Brendan Gregg and the Netflix guy wrote, right? This is something I could show them more if you guys want to talk about it, but this is the kind of thing that you can run in production without having to do any special Java stuff other than define these two flags. But once you have that, you can, like, in real time, if your node is doing something, you don't know what the hell's going on, you can actually run this and get like a really nice detailed snapshot. And these things you can click on and zoom in and search, and they're pretty cool. So I'm basically still in the exploratory phase because what I really want to find out, and this is the last slide, is what these show is sort of like your on CPU time. Like what is the CPU doing? But when you're doing something like compaction that's I/O intense, you really want to see what's happening off CPU. So there's this new thing which is really only allowed in the new Linux kernels, which this is why I suffer through running Linux, because I like to have access to these things. But if you run with a particular Linux kernel, this eBFP tracing language, you can actually write tracing code to run inside the kernel. And one thing you can get is you can get your basically off CPU method calls and which and when the kernel wakes it up. So you can see, and then you can combine these in a sort of on CPU, off CPU flame graph, which is accurate to time. So you can actually see like what the system as a whole is doing, whether or not it's blocking on like page cache faults or something like that. So this is kind of what I've been doing. The goal is to get is to basically improve our compaction by finding bottlenecks and doing a really detailed analysis versus like, I wonder if I try this and it will work, because that's pretty much the way that we solve a lot of these problems. So trying to do actual tools that will help us that are actually pretty generally usable for all Java systems. So this might end up being something pretty useful. That's all I have. Thank you. Enjoy your.
Almost an hour overtime because you guys suck at keeping your talks for 5 minutes. But we have dinner at 6:30 at the Parkside Restaurant, so that's in 10 minutes. So as quickly as you can drop your bags off or whatever. But in 10 minutes, it's just a block away, so it's like a 2-minute walk east on 6th Street, and it's going to be on the south side of the street. So freeway is east from here. So walk towards the freeway and cross the street south. All right.
Yes. Yeah. Let's do that. All right. So I got to dismantle. What's that?
Are you at the thing?
No, for our podcast. It's a really good microphone.
It's on.